Oh, I should turn the recording back on. Chase, you there? I can't tell if Chase is there or not. Are you guys all hearing me okay?
Yes.
Okay. I'm going to throw up my participants tab so that I can kind of get a handle on who all's here and not. All right. Chase, can you hear us? Click yes if you can. Yes. Okay. All right. You don't have to click yes if you can just answer yes. All right. So I think everybody is in. So today, what I want to talk to you about is basically non-parametric alternatives to ordinary least squares regression. So you will recall that least squares regression has the same kinds of assumptions that any other parametric statistical test has. And so there are non-parametric equivalents to this method, just like there are non-parametric equivalents to any other method. And I should capitalize rank. So this is a presentation that only has 4 slides because it's a really simple kind of process. So remember that when we do non-parametric tests, oftentimes we basically just convert the data to ranks. And so we rank the data from lowest to smallest. We assign 1 to the lowest and n to the highest value in a data set. And that's the same thing that this is going to be using as well. So this is a Spearman rank correlation coefficient. It's probably the most widely used. There's another very similar formula, set of formulas that will give you a thing called Kendall's tau. You might see that in some books. But Spearman, I hardly ever see anybody use Kendall's tau, and everybody who does this typically uses Spearman. Once again, I'm taking this information from a book called Applied Non-Parametric Statistics by a guy named W.W. Daniel. If you are ever interested in non-parametric statistics, this is a very good book. I don't know how many of you might be interested in non-parametric statistics. So anyway, you're going to use this whenever you need to measure the degree of association between 2 variables. And so in this way, it's just like ordinary least squares regression. But in this case, the ordinary least squares regression assumptions are not met. Typically, either the normality of the residuals assumption is violated or the homogeneity of variances assumption is violated. These are the 2 that we have no control over. And so if 2 things are going to typically be violated, it's one of these 2. And like I said before, this uses a rank transformation of 2 variables that are being examined. So how you do it is you basically rank the X data from 1 to N, and you rank the Y data from 1 to N, and you do that ranking separately. So you end up with 2 separate rankings. If you were doing this in Excel, I would probably set up a data file that had an observation number column, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then had X values that were X1, X2, X3, X4, X5, X6, X7, X8, and X9, and Y values, which would be Y1, Y2, Y3, Y4, Y5, Y6, Y7, Y8, and Y9. And so I would probably set it up this way. And then you can use the data sorting function in Excel, which I'm sure you're already used to sort these 3 columns on the basis of X. And then once I had X ranked, I would set up a column for the ranks, where this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I would go through and sort each of these columns on the basis of the y's, have ranks for the y values, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then I would go and sort all of these on the basis of the observation numbers to put the data back in the original order that they were in. That way you have a column of ranks for X, a column of ranks for Y. Each of them has been ranked separately. And then once you have them back in the original order, you can do the calculations. Does that make sense to everybody?
Yeah.
Okay. All right. Once you have this done, the formula is not complicated. You're basically calculating what keeps happening to my computer. You have Spearman's rho, which is R sub S here, and it's just 1 minus everything in this bracket. The bracket has a numerator that is 6 times the sum of d squared sub I divided by n times n squared minus 1. And so the d squared sub I, sum of d squared sub I, is just the sum of the differences between the X rank and the Y rank for any of those rows squared, all summed up across all of the different rows that you have. And this makes sense in a way because you're subtracting 1 from the equation here. But what happens is, in this case, I've made each of these things exactly opposite. The first observation in X was ranked 1. The last observation was ranked 9. For the Y values, the last observation was ranked 1, and the first observation was ranked 9. So for each of these things, they're exactly negatively correlated with one another. When you take 1 minus 9, that's 8. You square that, that's 64. These things are big at the ends, and these differences are big at the ends of the data set, and they're small in the middle of the data set. And what this indicates is that as you add up all of these squared deviations, these squared differences from one another, this whole thing summed up gets really, really large. Then, once you have scaled that by sample size, which is what the numerator does, it gives you something that is either close to 1 or far away from 1. And when this thing gets very, very large, this numerator gets very large, this whole thing gets very, very big. And as a result of it getting very, very big, when it's subtracted from 1, it takes it in the negative direction, and it reaches a value close to -1. And in this case, it's going to be exactly -1 because of the way I've structured the data here. So Spearman's R ranges from -1 on one end to +1 on the other end, and those are the theoretical limits of it. A -1 would be perfect correlation in a negative way, and a +1 would be a perfect positive correlation. So the equation is relatively easy to work. So we can go back to the confused beetle weight loss data, which is what I've been using as the example for all of these regressions. And one of the things that's nice about this data set is that it's small for one thing, and the relative humidity is already ranked. So if we were going to rank X, it's really easy. This is the first rank, second rank, third rank, fourth rank, fifth, sixth, seventh, eighth, and ninth. So finding the rank of relative humidity is relatively easy. And as it turns out, finding the rank of weight loss is also relatively easy. 3.72 is the first, 4.2 is the second, third, fourth, fifth, sixth, seventh, eighth, and ninth. And so as it turns out, this is exactly the situation that I drew on the board. So now that you have that, all you do is you subtract 1 minus 9, which is 8, square it, which gives you 64. 2 minus 8 is 6, squared is 36. 3 minus 7 is 4, which squared is 16. 4 minus 6 is 2 squared, which is 4, 0, 4, 16, 36, and 64. It will not always work out this nice and symmetrically. It just works out this way with this particular data set.
Dr.
If you
Klowinski,
have, yeah, go ahead.
I have a question. I'm sorry.
Yeah.
I understand the rank, but isn't the opposite for the rank of weight loss? Like 8.98 is bigger than 3.72. Shouldn't be that the first of the rank?
No, the lowest rank is always the smallest number. So for X, it would be 0 is 1, and for weight loss, 3.72 would be 1.
Okay, so the opposite of the first rank?
No, you rank X and Y separately. So you have relative humidity goes from the low rank of 1 to the high rank of 9. And weight loss goes from the low rank of 3.72 to the high rank of 8.98. In this case, the way the data were structured originally ended up putting them in this order, but normally you would have to go through and order them within each variable to create the ranks. It's just really easy to do it this way. These could have been in any order. It could have been 29.5 at the top, 12 where it's at, and 0 here, and then these ranks would have been 3, 2, and 1 in the relative humidity rank column.
Mm-hmm.
So within relative humidity, you rank the variables, the values from lowest equals 1 to highest equals n. And then within weight loss, you do the same thing. In this case, because these things are negatively correlated, the low values for weight loss appear at high values of relative humidity, which is why the ranks are opposite.
Okay, I got you.
Yeah, so go back to this. First, you rank the X data from 1 the lowest to n the highest. Then you rank the Y data from 1 the lowest to n the highest. Then you do your calculations.
Thank you.
Yeah, sure. So once you have all of these differences squared, oh, I was about to tell you about ties, sorry. So if you have repeated observations in your X and your Y data, you would do ties the way you do with any ranked data. You would add up the ranks that they would normally have, that they span, and then divide by the number of ranks that you have tied, and you get an average rank for each of those things. You would handle ties the same way you would handle ties in any ranking scheme. Once you have that all done, you sum that whole thing, the sum of these squared differences, and then you plug that sum of square differences into this equation right here. You would multiply it times 6. You would divide that multiplied that product by n times n squared minus 1. And when you do that for this data set, the number of observations that you have is 9. And so that would be 9 times 9 squared minus 1. And when you do that, R ends up being -1, which is exactly what you would expect if you had this sort of situation where each of these is paired in opposite directions. And so according to Spearman's correlation, you have a perfect negative correlation. So the lowest value of relative humidity is paired with the highest value of weight loss. The second lowest value of relative humidity is paired with the second highest weight loss. The third lowest relative humidity is paired with the seventh highest weight loss. And so whenever you see a data set that is structured like this, you should just intuitively guess that it's going to be -1. Then that's just the way this particular data set happened to have turned out. So that's how you do it. Any questions about the method?
Nope.
Okay, it's actually pretty easy. One of the things that I liked about non-parametric statistics when I took the class in this as an undergraduate is that they're actually in many ways kind of easier than the parametric methods in terms of the calculations. So I want to now go and look at the R script that I had worked on for analyzing this data set. So can everybody see my R output?
Yep. Yes.
Yes.
Okay, all right, cool. So I'm gonna make sure that I'm in the right place. So I'm in my R scripts file. I'm gonna load my libraries. I'm gonna add in the data file. I'm gonna look at the data file. The data file looks correct. We can do a regular regression on this. And I want you to pay attention to a couple of things. We've already seen this. Can you see the output clearly? Or do I need to blow it up?
I can see it.
Okay. So normally you can once again access the model results one of two ways. One way that you can do it is by typing summary. And once you get summary, what it gives you is the equation for the line, basically. So the equation for the line in this case, the y-intercept is 8.704027 minus 0.05 something, if I'm recalling correctly, 0.5322. 3222 times relative humidity in this case, and the y variable that we are predicting is weight loss. Okay, so this is the y-intercept and this is the slope. Oftentimes the slope in a statistics test will be referred to as the regression coefficient. And so the slope value is the regression coefficient. What we just calculated with Spearman's test is a correlation coefficient. I always spell correlation incorrectly. Correlation with 2 R's and 1 L or 2 L's and 1 R? Losing my mind. It's 2 R's and 1 L.
Yeah, I think it's 2 R's.
So a correlation coefficient basically is a measure of not how steep the line is, but how closely clustered the points are around the line. And when we get this output here, once again, you'll recall down here at the bottom, so it tells you whether the intercept is significant or not, and whether the relative humidity, whether the slope value is a good predictor of y in terms of the slope of the line, and it does statistical tests on both of those. You can see those statistical tests there. But then it has this R squared value down here. R squared is the coefficient of determination. And it's literally R squared. The correlation coefficient is R. So if you want to get what R is, and in an ordinary least squares regression, this is the Pearson product moment correlation. The Pearson product moment correlation should just be the square root of R squared. And so just put that in your bonnet for a minute. This whole thing gets tested with an F-test from an ANOVA table, which we've already been through how that gets calculated. And it gives us a p-value of 7.816 times 10 to the minus 7. So the p-value for this regression, 7.816, that's a very low p-value. That is a significant regression. So we can also look at it this way if we wanted to, looking at how much variation is explained by relative humidity. Most of the variation in this model is explained by relative humidity, which is why the R-square value (0.9745) is very high. Relative humidity does a good job of explaining variation in weight loss. And so this is the same p-value here that we see up here, 7.82 times 10 to the minus 7. We can go and look at the plot of this. The plot looks the way the plot always looks, which in this case has the line of best fit fitted through the points with a gray band indicating the 95% confidence interval of the slope around the line. I talked to you last time about how we can test for homogeneity of variances by doing a non-constant variance test, and it will give you, once again, a p-value down here. And we can also get a plot of the residuals to see whether or not the spread around the line varies as the fitted values goes up. We can also get a QQ plot of the residuals so that we can see if the residuals are very far from the line, and we can test the residuals with by looking at it with a histogram form, and we can also do a Shapiro-Wilk test on the residuals. And once again, the p-value here may be because the data are not really different from normal, or the p-value here may just be a function of the fact that we only have 9 values that are going into the test, so we don't have a lot of power in order to do this. So just to remind you what the data look like, again, these are the data. So down here, what I have is a set of new code that you haven't seen before, new scripting that you haven't seen before. These are 2 lines of code that basically ask R to calculate the correlation coefficient, not the regression coefficient, not the slope, but the correlation coefficient of the correlation between relative humidity and weight loss. And I just made a mistake. I moved something when I shouldn't have. In this case, the X value always comes first and the Y value comes second, which is just the opposite of how you have to specify it when you're going through and doing this. Whenever you're specifying the linear regression, the dependent variable comes first and the independent variable comes second. When calculating the correlation coefficient, the independent variable comes first and the dependent variable comes second. And then there are different ways in which you can calculate the correlation. You can calculate the Pearson product moment correlation, or you can calculate Kendall's tau, or you can calculate Spearman by just changing the name. And for Kendall, I think you just type in Kendall with 2 L's, and for Spearman, you just type in Spearman. So when we calculate the correlation coefficient, you see that the correlation coefficient is negative 0.98 71523. 71523 for those of you following along at home. And what I told you is that that correlation coefficient is just the square root of R. So if we take that value, which is negative 0.9875 7.9871523 and square it, we get 0.97446966, which is, when we look at the summary data, the summary from the other one, we see that the R squared value is 0.9745. So you can always get the Pearson product moment correlation by just taking the square root of R squared. And those things should give you the same numerical value. And then you have to put a plus or a minus on it, depending on whether it was a negative slope value or a positive slope value. As soon as you square it, you lose that sign that was on the Pearson product moment correlation. The other cool thing about this is that when you test that correlation coefficient for significance, pay attention to the F statistic down here with the degrees of freedom and the p-value. You see that that was 7.82 times 10 to the minus 7th. When you test the Spearman correlation coefficient, it's basically the same test, because once again, you see 7.816 times 10 to the minus 7th. So it doesn't really matter if you test the slope for significance or whether you test the correlation coefficient for significance. It's basically telling you, in this case, the exact same information. And then you just need to know the relationship between R squared and the correlation coefficient to figure out one from the other. If you are actually interested in what the equation is, then the thing that you're interested in is what is the slope value. But you should always be interested in whether or not variation in the X value is a good predictor of variation in the Y value. And that is always given to you by the coefficient of determination, which is R squared. Did everybody follow all of that?
Yeah, I think so.
Anybody not following? Okay. Well, we can rewrite the same little code and just change Pearson for Spearman, and it should give us the Spearman correlation coefficient. In this case, it's -1, which is exactly what we calculated, and we can test that for significance. And it is significant, but the p-value here is 5.51 times 10 to the minus 6. One of the things about non-parametric tests, which I've already mentioned, is that they generally are less powerful than parametric equivalents. And so the p-value here is not as low as it was for the Pearson coefficient. But in most cases, these two tests should be qualitatively similar. If you find significance with Pearson, you should also find significance with Spearman, unless your original data are really messed up relative to the underlying assumptions. So once again, almost anything that you can do by hand, you can do in R as well, and much quicker. And if you wanted to be fancy about all of this, you could actually go back to the original data frame, which is Beatles, and you could actually have R rank relative humidity and create a column for that. You could have it rank weight loss and create a column for that, and it should produce what was on the board earlier and what's in the PowerPoints as well. But that is non-parametric equivalence of regression. And like I said, it doesn't really tell you anything more than this is telling you. But in the event that there was a relationship between relative humidity and the spread of the points around the line, you would want to use Spearman rather than a normal ordinary least squares regression, because you violate the homogeneity of variances assumption. So when you look at regression data, you see certain patterns that crop up in terms of residual plots and things like this. In this case, we have a negative correlation. And what happens generally if that x and y axis goes from low values to high values and low values to high values, generally the higher a value something has, the more it's prone to vary. And so oftentimes what you will see is patterns of variation that look like this, where things with high values have more variation than things with low values in that y aspect. Same thing when you have a positive line, you'll oftentimes see that the variance in the data increases as the x value gets bigger. These would be violations of the homogeneity of variances assumption, in which case ordinary least squares regression could possibly give you the wrong answer. In most cases, when this happens, what it's going to tell you is that the regression isn't significant when it might actually be significant. And so what the violation of the assumption does is it causes you to lose statistical power to tell whether that slope is different from 0. The other assumption that we talk about basically says that at any given x value, the distribution of the data around the line will be normally distributed. At any given x value, the distribution of the data around the line will be normally distributed. At any given x value, the distribution of the y data will be normally distributed. This is how the normality assumption works in regression. You can't test that unless you've done replication at each of the x values that you have. And so what we generally do, and this will become important with the next topic that we cover, analysis of covariance, what we generally do is we calculate what the grand mean of x is and put a line there conceptually. Whatever the data points are that are around this line, we basically look at the residual value, how far away from the predicted line the data point is, and we essentially squeeze all of these data points down the line. We move them down the line like so, preserving their residual distance from the line. So we move these all down to the grand mean. We move these all up to the grand mean. And at that point, we have a bunch of points here at the grand mean. And we test that distribution to see if it's normal or not. This is why what we do when we do the Shapiro-Wilks test, we just basically calculate what the residuals are and then do a Shapiro-Wilks test on the residuals. That's how we generally test the normality assumption, because we only have one observation at 0 humidity. We only have one observation at 12% humidity. But that's exactly the kind of residual manipulation we do when we test Shapiro-Wilks tests for an ANOVA, whether it's a one-way ANOVA or a two-way ANOVA. So once again, there's something that I've tried to make a point on of early in the semester, which is that the key to mastering statistics is to learn a relatively few kind of key concepts, because we keep applying those key concepts over and over and over again, whether you're doing regression, whether you're doing ANOVA, whether you're doing the next thing that we'll tackle in here, which is analysis of covariance. They're all based on these same sets of ideas. Questions?
Dr. Glowinski,
Yes.
can you explain in short words what is the variance we're looking for in this data set?
Well, it's not run the way we normally think of as comparing variances explained like we do in an ANOVA. So let me go back here. Let me. So back when we were doing the ANOVA version of this, so this is ordinary least squares regression. This is the parametric method. We would calculate all these things because we're actually interested in finding the variation in the data that is explained by the regression line, and we are interested in what variation is not explained by the regression line. So we would actually calculate a ANOVA table that would show you the sums of squares that are due to regression, the sum of squares that are due to error, unexplained variation, and we would calculate an F statistic and test it that way. And so in this way, we're asking how much variation in Y gets explained by variation in X versus variation that's not explained. If, well, let me go back here. I went back too far. If all of the variation in Y was explained by variation in X, each of these dots would be on the line. This dot would be on the line, this dot would be on the line, this dot would be on the line, this dot would be on the line. And in this table right here, this table right here, that would be the value of Y at that value of X. That would be the value of Y at that value of X. 7.134 would be the value of Y at 29.5 relative humidity. That's what the line is telling you. If this was a perfect correlation, this dot wouldn't be a little above the line, it would be right on the line, and its value would be 8.704.
Yeah, I was about to ask that. So the line should be the perfect distribution of a data set, right?
Well, it would, if all of the points were on the line, R square would be 100%. If you have a correlation, you have a regression, this is the best fit line, and every point is on that line. Knowing about variation in X tells you everything there is to know about variation in Y. If you know what X is, you know what Y is. There's no uncertainty. And in this case, R squared would be 1. The Pearson product moment correlation would also be 1, but in this case, it would be a -1. And this is the Pearson product moment correlation. But Spearman then would also be 1, because this would be on the y-axis, this would be the highest. So I'm going to put y over here and x over here. This would be the highest y number, but the lowest x number. The second highest y number, the second lowest x number. 7, 3, 6, 4, 5, 5, 4, 6, 3, 7, 8, 2, and 9, 1. So this would also then be the Spearman correlation coefficient would also be -1. And so all of these things would all match up if the data were exactly on the line. But in this case, the line doesn't perfectly predict what the actual observed values are. So we have this residual variation, the variation that is not explained by the line. How far does this actual data point here differ from what would be predicted by the best fit line? That variation goes into forming the residual variation. So this is sum squares residual. It's simply the predicted value minus the observed value. So 8.98 minus 8.74 squared gives you this value here. That's the amount of, that's the amount of variation that is not explained by the line. Y hat is the predicted value. It's the value, of the line compared to the overall mean, which in this case was like 6.022. And what that tells you is how much does the predicted value vary from a slope of 0 line, a horizontal line going through here. How much, I have a graphic of this back here, how much does this value differ from the mean weight loss? If this value is big value difference between here and the 0 line, 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 basically tells you that the line deviates a lot from a slope of 0. So as a result of that, the deviation of the predicted value, which is y hat, minus y bar, which is the mean value of 6.022 here, that difference squared gets to be really, really big because the slope of the line is important in describing the relationship between x and y. And so you can evaluate this with a ANOVA table by looking at how much variation is accounted for by the linear model divided by how much variation is not explained by that linear model. And that's actually where we get sums of squares for regression, sums of squares for residual, the mean squared, the F value, etc. Does that make sense?
Yes, absolutely.
Now, when we, I haven't actually answered your question yet. So when we take these values and convert them to ranks, we get rid of all of that residual variation. So if one of the assumptions that was violated was that the variation isn't similar across the length of the regression line, if variation is higher at low values of x than it is at high values of x, we don't have constant variance. But as soon as you convert these things to ranks, you don't have to worry about that variation anymore. So in this case, there really is no residual variation. It's just, is the correlation significant or not? Are the two things related in a positive way, or are they related in a negative way? And so when you do the correlation test, you don't actually get an ANOVA table out of this. What you get is you get the sum of the differences, which is 240, which is exactly what the sum of the differences were in our example here. Let me pull it up again. We get the sum of the differences, which is 240. That is right there, so you can check your own math. And we get the same Spearman rank correlation coefficient that we had before. But basically, that's just asking over here is, what's the rank of this y value compared to the rank of the x value at the same point? What's the rank of the y value versus the rank of the x value? Rank of y versus rank of x. Rank of y versus rank of x. And here, they go down in sequence. 9, 8, 7, 6, 5, 4, 3, 2, 1 in the y space, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 in the x space.
I
So they're
completely
really
understand your explanation. I was just concerned about like losing the power of my data set by ranking my points, my individual points, you know?
Yeah, so you do lose some statistical power. That's a valid point, and it's a point that can be applied to any non-parametric test. But what it gains you is, let me draw this better. If this is your regression line, the same regression line that we have here, and if the 95% confidence interval of the slope in an ordinary least squares regression looks like this, well, I didn't draw that very well. Sorry. I'm a terrible drawer. Where it's much more variable at low values of x, and it's much less variable at high values of x, what can happen sometimes is that won't appear as a significant regression, because depending on how wide this band is, you might not be able to fit a slope of 0 through that regression band. I've drawn it in this case where you can, but that's also a fairly steep regression. Imagine that if you had a situation where the regression line, which I'll draw in black, if you had a less steep regression line and you had really tight variances at one end and those variances really spread out at the other end, the question becomes, where along this line do you test for this thing having a slope relative to 0? Are you testing whether or not the slope is different from 0? Do you test it down in this narrow band where it's very difficult for you to get a slope of 0 fit in that range? Or is it tested out here where you could fit a variety of slopes inside those confidence intervals of the slope? And so it's similar in that way to the same problem that you have with ANOVA when you have treatment A and treatment B. You have some Y response variable. You have the mean of A. You have the mean of B. The mean of A has a relatively small 95% confidence interval, but the mean of B has a really large confidence interval. How do you decide whether or not those two means are different? Because this mean could have come from this population, but this mean could not have come from the other population. It's an analogous problem. And so sometimes when you violate the assumptions of a parametric test, the non-parametric test actually has more power than the parametric version because it doesn't make the assumption about equal variances across the length of the regression.
Okay.
But if you satisfy the assumptions of the test, then the parametric method will usually be more powerful than the non-parametric method, which is why people typically use the parametric method rather than the non-parametric method. Does that make sense?
Yes, thank you.
When thinking about regression and ANOVA, think about the ways in which they are analogous to one another. The homogeneity of variances assumption in many ways works the same way in a regression as it does in an analysis of variance. Same thing with the normality assumption. And when it comes to generating a statistical test of the correlation in the ordinary least squares way of doing things, not the non-parametric method of doing things, what you get is you get an ANOVA table out of the deal. It's a slightly different ANOVA table in that it's asking how much of the variation is due to, in this case, the regression model that you're testing versus how much is unexplained. But this is also a regression model as well, how much of the variation in y is explained by whether you're in treatment A or treatment B versus the amount of variation that is not explained by being in treatment A or treatment B. Same ideas. So concentrate on this kind of universal way of thinking about statistical testing. And then that gets applied in slightly different ways across a variety of different methods, but the same basic concepts are all still there. Questions? For next time, because we're done here, if you guys have no questions, we're going to be talking about multiple regression. There are actual page numbers in the course schedule for what I want you to have read for Friday. I'm going to introduce you to the ideas of multiple regression. I'm not going to have you work any problems because at that point, the calculations actually become quite hairy to work them by hand. But what I do want to do is I want to take you through multiple regression, how it works, what it can be used for, and things like that, so that you're at least aware of it. In many ways, it's not really that different, except that instead of having one x value, you have multiple x values that might be predicting a particular y value. So it's good to read about it. I'll take you through an example on Friday, but I won't have you do any problems with multiple regression. And your write-up on regression will actually be a simple ordinary least squares regression. And after we're finished with that, then I'll have your other things graded and back to you, and then I'll assign the assignments for linear regression on Friday probably.
When will those be due?
Not sure. I'll think about that between now and Friday. So you have two sets of things still to do. The linear regression stuff, which I'll have a problem set for you to work on by hand, because it's not that hard. Probably it's going to have a reduced number of problems because if you recall from regression, you're basically trying to estimate these two things. We're basically estimating this, which is all inside of that. So the estimation problem is not as complicated as like a two-way ANOVA. So it's pretty easy to master. And then there's going to be a written assignment on that, a report continuing to look at Gecko data, but now you're going to look at Gecko data in a regression sort of way. And I gave you some inklings into that because there's a new column in the Gecko data this last time that you ignored because I didn't ask you to do anything about it, but we're going to actually start working with that other column for the regression thing. And the reason that I'm having you kind of look at the same data set in a variety of different ways is because it's a data set that lends itself to looking at in all of these different ways. And so that will be due before the end of classes, but I'm not sure how much time I want to give you on that, but we have some leisure there because then the thing that we're going to be covering while y'all are working on that is analysis of covariance. And analysis of covariance is a weird conglomeration of both linear regression and analysis of variance. And so you need to know about regression and you need to know about analysis of variance. The calculations for that actually become very complicated. So we won't have a problem set on that at all. We'll just actually have a final write-up on that. And so there'll just be a data set that you will analyze in R for the ANCOVA, and that will be due on the day of your final. So there is no final exam. There's just your final write-up is due. So we have how many more weeks left in class?
Probably a month.
Yeah, about a month. And basically there's one problem set, one write-up on regression, a regression problem set and a regression write-up. and then the final analysis of covariance write-up. So we have plenty of time to get all this stuff in. Does that make sense?
Yes, sir.
All right. Nice chatting with you. I'm glad that you guys are all healthy and not wanting to kill your families. And I'm going to get back to grading and hopefully get grades posted sooner rather than later.
Okay.
All right. Email me as always if you're having any difficulties. And I'll see you on Friday to talk about multiple regression.
All right, sounds good.
Thank you.
Friday.